Okay. Well, we have a brief little slideshow that we will be going through, just some really simple details about the rocket in its current state and what we're expecting out of it, and then we'll open it up for any questions or discussion you might have.
Okay. Hi, Bill. Oops, you're on mute. Now you are.
Oh, okay. All right.
Okay. You see this all right?
I sure can.
All right. So yeah, we'll be going through the safety review. Just an introduction. We'll have everybody introduce themselves when they come up here. I'm Andrew Barloon. I'm the project lead for this year. We'll also be the flyer of record. So we'll start with our Vice President of Engineering talking about the overview of the rocket and the simulations we've done.
Hey everyone, I'm Jake Blocker. I'm this year's Vice President of Engineering. So going over the rocket overview. So this year our rocket's name is Intrepid. It stands at roughly 16.7 feet tall, or a little bit less than 200 inches. It has a diameter of 6 inches. It weighs roughly 137 pounds in the pad, and after burnout it's 105, so about roughly 32 pounds of ammonium perchlorate composite propellant, which we'll talk about in a future slide. Our liftoff stability margin is 1.2 calibers. At burnout, that is 2.5 calibers. We are simulating an apogee of roughly 30,700 feet. I have the asterisk here because we are simulating to that, but with our air brake system, we're trying to get as close to 30,000 feet as possible. So we have that 700-foot margin that our air brake system has to roughly scrub off. And this is, at this 30,000-foot apogee, we're going roughly Mach 1.5. And this rocket uses an ESRA 4600 motor, which again will be talked about on our propulsion slides. And it is a minimum diameter 6-inch rocket. So you can see on that schematic there, the motor has the boat tail integrated, and that slides up to the booster tube and is retained by a bulkhead that sits right below our air brake module. So a concept of operations. This rocket is a little unique in the sense that it is a single deploy. So we take off. We have motor burnout roughly 8,500 feet above ground level, where we coast with our air brakes to 30,000 feet ideally. At apogee, we deploy a reefed parachute that is just below the nose cone. So we fall from 30,000 feet at roughly 90 feet per second with this reefed parachute configuration. And at roughly 1,200 feet, we blow a line around our parachute. We disc-reef that line, and that allows the parachute to open up fully, which allows us to hit the ground at roughly 20 feet per second. And this whole parachute system will be explained in much more detail on upcoming slides. So some of the simulations we've been using this year. So we've really emphasized a lot of testing and simulations this year. And we've used three separate simulations to converge, or we've used three separate simulations, and they've all converged to within roughly 1,500 feet. So we figured that the more simulations we could run on this rocket, the higher fidelity results we can get. So we've used a combination of RAS Aero, that is that graph in the bottom right. You can see roughly 32,500 feet. We've used Open Rocket, which is around 31,000 feet right now. And we've also used a home-built MATLAB script to be able to compute our apogee as well. And all of these, again, converge. And all are roughly above 30,500 feet, which again is because we want to scrub the rest of that apogee with our air brake system. So now moving on to our aerostructures team. Oh, we'll take it.
All right, hi everyone. My name is Will Hafer. I'm the aerostructures team lead. So I'm going to talk about the airframe of the rocket for a little bit. So the airframe of the rocket this year are filament wound body tubes. We use a machine called the X-Winder for that, and the pattern that we decided to go with this year was a hoop for the first layer and then 3 more 45-degree layers. The reason why we did this is because we had to use thick mylar. All right, we had to use a thick mylar to add a little bit more of a diameter to our body tube so we could get our motor case in. So the hoop kind of presses down that thick mylar so it reduces any ridges coming in from that. And then the reason why we did 45-degree layers is because those are most optimal for compression. And we did some Instron testing in the fall and this spring. That was compression testing using an Instron machine. In the fall, our first sample that we did resulted in 27 kilonewtons of force was the failure point, and then the sample 2 through 4, we actually ended up maxing out the Instron machine. And the reason why those are so different is because for the second one, instead of using our manufactured bulkheads for the Instron testing, we had to use just kind of like steel blocks to push against it. But that sample, the sample 2 through 4 is still accurate. And then that brings us to a minimum factor of safety of around 6 for the first sample and around 9 for samples 2 to 4. So for our couplers, we have 3 couplers this year. We do a layup on a FEMA mold, and that was 4 layers. No, that was 8 layers. Sorry, 8 layers, and all of the sides go in at least a body caliber into our body tubes. And then for the fins, they are 1/4 of an inch thick with a fiberglass core with 2 layers of carbon fiber on each side and metal fin edging. To keep them attached to the rocket before we did the tip-to-tip, we put inch-thick radius JB wellets. And then we did a 4-layer tip-to-tip over the fins. So that included plies that were 0-90, and then also 1 ply that was 45, -45. And the reason why we included that 45, -45 is because it helps significantly with divergence, which our divergence is 1.69 Mach, and then our flutter is 2.3 Mach. That is what FinSim gave us, but since you can't include a tip-to-tip in the simulation, our flutter and divergence will be much higher. And yeah, that's all I got. So, all right, and moving on to pistons.
I'll hold on my questions that I might have until the very end, so you don't have to wait on me.
Okay. Hi, everyone. I'm Jacob. I'm the mechanical team lead this year. And so for this year, we focused on having a piston ejection system. It is an all-aluminum piston design. It will be powered by 2 RRC3s. That way we have redundant electronics. The primary charge for it will be 0.7 grams. The redundant charge will be 0.85 grams. We have ground tested the system multiple times. We started off in the fall with ground testing, and then we did ejection test of our cup rocket this year, which is on the screen here. And so this was the first ejection test of our cup rocket. We are planning on doing a couple more ground tests or ejection tests of our rocket to ensure that the piston will eject. We also have flight tested the piston system 3 times, so we know that it works in flight. Up next, for piston wiring, the way we have a redundant system is the charges are completely separate within the piston. Each one goes back to its own RRC3, which each has its own 9-volt battery and magnetic switch to turn it on. So they are 2 completely separate systems. Next is our parachute.
Hi, so my name's Hunter. I'm the recovery team lead. So this year we have a fully SRAD parachute. So we manufactured the whole thing in-house. The geometry we went with is an elliptical parachute. We went with this shape because it's efficient. Previously we had done cruciforms, which had tangling problems. Also for reefing, since it's circular, it works out better to constrain it with the reefing line. So the minor major axis ratio we went with was 0.707. It has a 13-foot canopy diameter with a 20% spill hole, which goes up to 2.6 feet. It's made of 12 gores. We did subscale testing with the same parachute geometry with a 48-inch parachute and a smaller high-power rocket, and we use that to estimate a CD of 1.4 with the parachute. This brings our rocket down at about 20.2 feet per second. It's manufactured using 1.2-ounce ripstop nylon, which is calendared, and we used a size E69 bonded nylon thread to stitch the whole thing together. So for reefing this year, the way it works is we have a reefing line that runs around the skirt of the parachute. We also have 3 pouches that are located on the parachute gore centers, equally spaced around the bottom of the parachute. The reefing line also runs through. Inside these pouches are our reefing or disreefing devices. Two of them are powered with ESRA altimeters that we made. That's that picture you can see on the left bottom there. And the other one we have using a stratologger or COTS altimeter to satisfy the cup requirement. These devices, they are capable of cutting the reefing line at 1,200 feet to release the parachute and let it fully open. And we use RF switches to wirelessly activate these devices on the pad since they're inside the parachute and the bag in the rocket. We have ground tested these as well as flight tested them twice where they successfully disreefed the parachute both times.
Okay, I'm back again. For our air brakes this year to help control our altitude, we use the Avionics electronics in order to control the, they control the air brakes. We use a servo in the center that's connected to a gear hub. The servo turns that gear, which is connected to the brass racks, and they push the bottom of the air brakes out. They're allowing our air brakes to open and deploy. They were designed with the first point of failure being those brass racks. So that way, if something were to happen, the air brake would fail closed, and therefore we wouldn't have an air brake get stuck out and then our rocket be going off its course that we would like. And so this year we did some weight optimization on them to get them a little lighter. We did FEA on all the bulkheads in order to make sure that they could still withstand whatever force they would be taking. Next is our avionics.
Hi, my name is Mitch Jensen. I'm the avionics team lead this year. So as Jacob just talked about the mechanical side of the air brakes, I'm in charge of the avionics that control those air brakes. And our goal is to predict apogee based on the sensor data that we acquire and use that to actuate the air brakes to hit our target apogee. A few things that I'd like to highlight are our software ensures that the air brakes can only be deployed during the coasting phase of the rocket and only after we are below a velocity of 0.7 Mach. Additionally, in the event of a power cycle, our air brakes are designed to remain closed for the duration of the flight, just in case we have something go wrong with the bumps that the rocket might experience on the way up. That way, if worst comes to worst in terms of the air brakes, we just end up going a little bit higher than we'd like. And as you can see here, this is the design of our boards, and on the right side of the screen is our circuit diagram. You can see the battery connector in the bottom left corner of the circuit diagram there, and that is how we will be connecting the battery to the boards and the screw switch on the outside of the, key switch on the outside of the rocket that we will be using to arm these devices. Additionally, we have our COTS GPS trackers here. Both of these are needed to comply with the ESRA regulations for the cup. We're going to be using a Altus Metrum Telemega and a featherweight GPS tracker. We've used these on numerous flights in the past, and we have found that these are the best ones that we have found. These are going to be mounted in the fiberglass nose cone via a fiberglass mounting sled. That way we can maintain radio contact with these devices throughout the duration of the flight. Up next, we've got the payload.
Hi there, my name is Andrew Drazen. I'm this year's payload team lead. So for the experiment for this year, we are doing a fine particle measurement experiment. So we'll basically just be measuring fine particle concentrations in the air. The form factor for this year is a non-deployable 2U CubeSat form factor. It consists of 4 steel side plates and 2 aluminum top and bottom plates, and the weight of that is right around 9.5 pounds. The payload is mounted right inside of a coupler. It is mounted on 2 3/8-inch steel threaded rods that run through the coupler and connect to the bulkheads on each side of the coupler. Air comes through a hole in the coupler switch band to access, or for our experiment to access fresh air. We will also be attempting ground communication by transmitting data with a 433 megahertz LoRa module. And the antennas for that module are mounted on the outside of the body tube below the coupler and those wires or those antennas are thin wires which will be secured underneath the wrap of the rocket. Next up is Jacob Pittman to talk about the motor.
Hi, I'm Jacob Pittman. I am the propulsion team lead. So our motor this year is a 152 millimeter diameter motor. It's called Medusa. So our total impulse of this motor is 35.6 kilonewton seconds, burns for around 7.5 seconds. The total mass of the hardware of like nozzle, bulkheads, and the case is around 36 pounds. The classification of this motor is a O4642 and is around an 87% O. So the retention to keep the bulkheads in for this motor, we use 1/4-inch shoulder bolts. So these bolts are really precise and they distribute the load like really well. So that's why we decided to go with those. And the lowest factor of safety of this motor is greater than 3. So kind of an overview of what the inside of the motor looks like. So we have our insulation, forward insulation, and our nozzle are all made from the same material. It's made of CE phenolic, which is a great insulator. As it heats up, it ablates away to prevent it from getting too hot. Our case is made of 6061 T6 aluminum, and that is the same material used for the bulkheads just bulkheads. So as you can see there, kind of have the bolts on the front. And this motor has also already been static tested, and you can see our thrust curve right there, and it performed perfectly. And should have plenty of juice to get us up to 30K. So I'll move on to testing.
As you can see, we have some pretty ambitious and pretty sophisticated systems with piston and reefing and the air brakes and all that. One way that we've been able to build confidence in this is through a lot of flight testing. While Intrepid itself has not been flight tested and will not be flight tested for the Cup, we built 2 different test vehicles we've been using to test all of our subcomponents at various HPR launches around the Midwest. That one on the right there, the orange rocket, is called Skyride. It's a 6-inch diameter airframe, relatively the same size as our competition rockets that we've flown in the past. Actually allowed us to test actual flight hardware, such as the piston, in these flight conditions. Skyride has had 3 flights to date this year. One was just for piston ejection, where a drogue parachute was deployed by the piston with a main deploying shortly after to ensure that even in the event of a piston failure, we still got the rocket back. And then after that was successful, we had 2 flights of piston reefing, where the piston ejected the reef main in the exact same way that it will on Intrepid. But there was a secondary main that would deploy in the event that the parachute did not disreef. Both of those flights were also successful. We saw a disreefing event and saw what we were expecting to. Skyride will be flying again this Sunday at a launch event up in Fort Dodge, Iowa. This won't have piston or reefing on it. It will just be there to test our air brakes to make sure that they deploy safely and that the avionics and the code and everything works to get us to the right altitude. Then we have Marv, which is a much smaller vehicle. It's just a 3-inch diameter 54 millimeter motor mount rocket. We fly it on an L1000. And it's to test the built-in Mach shielding into our avionics. So since we'll be going above the transonic range on our way on Intrepid, we want to make sure that our avionics, since it uses barometric data, isn't getting confused by any pressure changes. So we have a state built into our avionics during our flight that will essentially ignore barometric data and start switching over to an IMU. This flew once in November, and we'll be flying our flight ready code this Sunday on that as well. So with that, we'd love to open it up to any questions. We'll also have a camera around that can get any close-up pictures of the videos of the rocket. We have everything around with us here. So thank you so much, and love to hear any feedback.
Guys, this was done very professionally. Thank you. I really appreciate it. There's one thing that this is missing, and that is an open rockets picture of it. Do you by chance have one you could show me? Given how complicated things are.
You have one? Yeah, we have someone looking for it now.
Okay.
We do have one.
All right, while you're doing that, and I do want to see the rocket, so it's your choice as to what you want to do from here. But I basically have a question about the JB Weld. I'm really curious why you were using that as your epoxy, and and also what versions of JB Weld you were using. Um, and then we'll talk about the reefing system a little bit. And the other thing I noticed is that based on your static test data, you have a burn time that's right around 7.2, maybe 7.3 seconds. But your burn sim was showing a lot shorter burn times. And I was curious if you can tell me why there would be a big difference.
I'm sorry, can you repeat that? What your question is?
Which one? Motor?
Burn sim.
Burn sim. Okay. The burn sim that I looked at, which was the one that was sent up on for your second report,
Yep.
has a burn time that I believe is, I could actually hold on a sec here, that is showing 4.9 seconds with a 95% efficiency. And yet your static test shows a burn time of 7.5 or close to it.
Yep.
Do you know why?
So,
By the way, everything else basically matches. So it's kind of like an anomaly.
yeah, so, like I was talking about, kind of as going over my presentation, phenolic erodes, it kind of like flakes away as it heats up. And we've simmed out our erosion pretty well on previous motors, but those motors were smaller. So we're thinking as we scaled up, it was just eroding away the throat of the nozzle a lot faster. So our pressure dropped faster. So the motor burned for a longer amount of time.
That's an excellent point. So you haven't taken advantage of the erosion capabilities within BurnSim then, right? You haven't
Yep.
tried to calculate your erosion?
Yeah, so we tried to use our erosion. It's just it was or we did include it in our sim. It was just a little low for what we actually experienced.
Okay, very good. That definitely explains it
Jacob, do you think that
on
could
that end
possibly
of it.
be?
So, okay. The JB Weld question, or go back and let's review the reefing and what happens if it doesn't work.
Yeah, Will can talk about the JB Weld real quick.
So the reason why we picked the JB Weld for doing our fillets is because that's what we've used on past rockets, and it's been extremely strong. It's very rarely chipped when even if it's gone ballistic and hit the ground, you can still see the JB Weld still attached to the rocket. So that's why we picked it for ours. It's very strong, and we used the JB Weld standard steel. So we didn't use JB Quick or anything. We used JB Quick to put the fin onto the rocket and hold it there so we could do our fillets. But that JB Quick is not structural in any way. The JB Weld is the structural part of that. So does that
Okay.
answer your question?
There are many versions of JB Weld. Which one did you wind up using?
Yeah, we used the standard steel version. So.
Okay. All right.
All right.
Okay.
You had a reefing question?
Yeah. The obvious question is, did you calculate your? I guess you actually did. You calculated your descent rate space if you don't reef, if the reefing system fails.
Yeah, so
You're coming in about 90 feet per second, if I remember right.
that's just our estimate based on like the relative drag when it's reefed. We actually, if I expect anything, it would actually probably be a little higher than that, just because the parachute's so massive. Even when the diameter is constricted all the way, there's still a lot of drag just from the parachute streaming, essentially.
In other words, a big streamer.
Yeah, yeah. There is still some drag from it because there is. We're constricting it down to 15% of the diameter. So there still is a little bit of air that can get in there and a little bit of surface area that's still acting as a parachute. But then also, yeah, it's a lot less than when it's fully inflated.
Okay, maybe if you can flip to the slides and flip to the reefing section for me. Yeah, perfect. Okay, those little boxes, where do they reside?
Yeah, so I have them here as well. I don't know if the camera is being shown right now, but so these boxes are located in small pouches. that run along the skirt of the parachute. So they're like little zipper pouches that have holes on each side. So the reefing line runs around. The reefing line also goes through small loops that are at each shroud line connection. So it goes through all these loops, and then it also goes into these pouches, which are located every 4 gores on our 12 gore parachute. So there's 3 boxes in total, 3 pouches. Inside those pouches are these boxes, which have a line cutter and an altimeter and a battery in them.
Okay. So I guess what I'm trying to make sure of, because what some people have attempted is the controlling electronics is still within the rocket, so they run really long wires out and hope like hell nothing gets tangled, yanked, or whatever. I'm getting the impression that these boxes or this packaging that you're doing will be outside of the body tube then, right? So the wire runs are all restricted to within that case.
Nope. So actually, we've tried before and seen other teams do a lot of different types of reefing, where you have reefing lines running up shock cord, you have wires running up shock cord, all that kind of stuff. And we wanted to make sure none of that was happening. We wanted everything to be contained. So inside each of these pouches is one of these boxes. In the box is the battery, the line cutter, and the altimeter, and it's all contained in these boxes with an acrylic cover. And they're activated wirelessly. So there's no wires running outside of the boxes at all, so they can't get tangled in any way with anything.
Okay, and when you say activated wirelessly, you're talking about the fact that they're turned on wirelessly, correct?
Yes, yeah, we have RF switches that we use to activate it when it's on the pad.
Okay, what kind of wireless switches are you using?
They're RF wireless switches.
Is something that you've made or off the shelf?
No, they're COTS. We ordered.
Okay. What's the altimeter?
So the COTS altimeter we have to satisfy the cup requirement of having a COTS altimeter is a stratologger. And then we also took on the project of making our own ESRA ones as well. So 2 of the boxes have our ESRA altimeters, and then the other one uses a stratologger.
Okay. You still didn't really answer my question on the RF switch.
Sorry, could you repeat it then?
The RF switch you're using for power on, power off, is that something you made or is it off the shelf or?
No, it's COTS. It's off the shelf. Yeah, we purchased it.
What is it?
It's not a name brand switch. It's just an RF switch. It uses a mechanical relay. We made sure that it was going to be flight ready because the
how is it activated? Don't tell me an RF.
it's activated with an RF transmitter.
Okay, so this sounds like please don't tell me this is like a door opener or something.
Door opener?
Yeah, garage door opener. You push the button and the door opens.
I mean, it's a similar thing. Can you describe why that would be an issue?
Well, I'm curious about frequencies.
So the range on these receivers, since they are inside of the body tube, which is made of carbon fiber, they can only be activated if the RF transmitter is placed up against the hole in the body tube. They're all within the 433 megahertz range.
How do you know it's been activated?
The altimeters begin to beep.
They what?
Begin to beep.
They begin to be okay. The altimeters will beep. That's what you're saying.
Yep.
Okay. All right.
Activate,
I put you through it. My guess is when you go through safety review at New Mexico, you're going to be put through the same drill.
Okay.
Okay.
Yeah, activating these switches figuring out how to wirelessly activate these boxes was definitely the biggest challenge we had this year. Because obviously you can't use.
What would happen if the guys in New Mexico decide they don't want you to do that? You can't use that type of technology to set your switches off. What are you going to do?
And I guess we can't fly. We had this approved multiple times in our progress reports. This is the design of our rocket, so I would hope that it'd be approved in New Mexico.
Another possible alternative to this, in the event that it's a hard no, is these fall below the threshold of what is considered energetics, and therefore can be activated before the vehicle is upright. Meaning, a possible solution would just be to power them on when they're integrated with the rocket, and then they would be on while we're setting everything up, but they won't do anything until after a launch is detected.
Okay. All right. I'm not trying to be hard-nosed. I'm not trying to give you a hard time. I just want to make sure that there are no surprises in New Mexico for you. Okay. Now, let me back. I'll ask one more. When we just back one more time.
Yeah.
You mentioned that it already had been approved by who?
What?
It was part of our previous progress reports, and we didn't receive any questions or concerns about that at the time. I think that's what we meant by that.
Okay. All right. All right. Okay. Again, not trying to beat you up or anything. Just be aware that there will probably be some questions about that. So, and we covered the burn time. We covered the reefing. Oh, just one other quick question, and then I'd like to go back and see the copy of the open rocket, please, and then I need to see the rocket too. Burn time. Oh, I assume that your payload is internal and therefore secured such that any kind of a recovery shock or whatever is not going to shake it loose.
Yep. It's on its own threaded rods within its own coupler.
Okay, cool. We can see the open rocket real quick. That would be great.
Yep, I got it right here.
I sent the picture if you actually want to find it.
This is the picture. If you actually want to see the file,
oh, you did it that way. I just wanted to see how the components were laid out. Like where your air brake's at, all that kind of stuff.
yeah, we actually can show you that on the rocket itself.
Okay, all right, let's do that then.
Okay, so I'll stop sharing my screen, and then we will use Jake's camera here for any close-up stuff here. So I'll mute myself. Jake,
Not necessarily an easy thing to do.
Yeah.
Say, Ben, can you hear me or am I muted?
No, I can hear you.
Okay. Would it be Bill Hansen? Is that someone I could run this radio frequency stuff through the RF things?
Video frequency. What?
No, the RF. You know, you're concerned with the reefing. Is that a question for Bill Hansen?
Maybe.
Okay.
I don't know for sure. It's I think we can ask Bill, and the other thing we can do is actually not Bill. I'd run it by Ken.
Okay, Overton.
Safety.
Yep. Okay.
They're going to be the ones that are going to complain about it if there's going to be any kind of complaining.
Okay.
A lot of these off the shelf, those kind of switches are sort of on the flaky side. So anyway, okay, let me see. I can see over there.
Yep. Would there be anything you'd like to see specifically, Ben?
Mm-hmm.
Okay.
What is the length of your shock cord?
All right. Can you guys hear me? It's on. Oh, you can. There you go. Hey. All right. I assume you guys can hear me now. All right. So yeah, this is the booster tube. So this is going to be sitting at the bottom of the rocket. So this is almost complete. The only thing we have yet to put in are these fin edges that our aerostructures team lead Will talked about. So the carbon fiber layups and the fins are all put together. You can also see our motor is integrated within the rocket as well, including the nozzle. The only thing that's actually not in here is the propellant itself. We have our rod there, and then we also have, these are the bolts that retain the motor itself. And sitting, to answer your question, Ben, about the air brakes, The air brakes are sitting right above the motor, so they would be right here within the rocket. So the pads would deploy right about here. Those holes have yet to be cut, but they will be soon. And then right underneath, this is where our avionics coupler slides in. So that coupler is this one right over here. So they each go in a little over 6 inches into the body tube itself. So this would slide into there. Then moving up the rocket, we have our camera or payload tube. That is what this is. Our payload lead, Andrew, was talking about wires that are being used to transmit data wirelessly during descent. And you can see those wires integrated within the tube itself. So this goes directly above the booster tube. And then on top of that, we have the actual payload itself. So this is the payload coupler that the payload would sit inside. So right now, the payload is just right here. Whereas in flight, it would be sitting on these threaded rods right here. And then moving up is the recovery tube. So this is where the actual parachute sits. It's our biggest tube, but yeah. And then on top of that, we have, of course, the piston ejection system, which can be seen over here. This is our piston. So on top are the fiberglass sleds, which our RRC3 electronics will sit on. And then this is the piston itself. So this pushes upon a switch band that's inside of the recovery tube to separate that nose cone. And then I guess last but not least, we have the fiberglass nose cone itself to make sure that our GPS electronics can actually communicate. And that is right here. So that's our fiberglass nose cone with our aluminum tip that we've all made ourselves. So if there's any questions, Ben, I'd be happy to answer any.
Yeah, I just have a curiosity question. Go back to your piston and flip it over so I can see the electronics and the battery holder.
I can't hear it.
Yeah, flip it over so you can see the electronics.
Yep.
Okay, so you do have tie wraps going across that battery holder to make sure it doesn't pop out?
Yes, we do. We do.
Okay, cool. The other thing, just a real quick question. How long is the shock cord?
How long is the shock cord, Hunter?
60 feet total.
60 feet total.
I'm sorry?
60 feet total.
Good. All right, perfect. Okay. Leo or Lee, you joined us. Do you have any questions?
No, I think you covered most of them there, Ben.
Yeah, I agree. I think this was an excellent presentation. I'll reverse the tables. Do you guys have any questions for me?
Any questions for Ben? I don't think we have any particular ones right now. I think, Bill, you said you'll be reaching out. We'll be reaching out to some people, other people within ESRA about those RF switches.
Sure, might as well. I do like your workaround though, Andrew, that if for some reason they weren't going to let those fly, literally, that you would go ahead and turn those on when you integrate the rocket, because you know, they're not considered energetic.
Yeah, there's not supposed to be anything turned on until you get to the pad, though.
Yeah, the design, I believe it's the rules and requirements or design and testing regulations. I can't remember the name of the document. Does specify line cutters as not being energetic, and they're not necessarily restricted in that way.
Yeah, yeah. I mean, I'll be honest with you. I'm not worried about the line cutters. I am worried about somebody, that may say, I don't like that RF and that switch, so on and so forth. Since, well, I don't know if you can get away with it or not, but I believe the electronics in that reefing system were all barometric, no accelerometers.
Yes.
Yeah, there's no reason it can't be armed when it's flat. And doesn't, but be careful of that, because you'll get people who don't necessarily totally understand how these components work, and they'll come unglued. So yeah, again, it's a caution. I think it's worth checking with Ken Bill. Get his wording on it, and and don't avoid it. Tell us exactly what you're using. Okay, don't beat around the bush. And you know, between Bill and I, we'll run it up to the safety guys and see. I just want to make sure that you don't get there on Monday afternoon and be told, sorry guys, you know, come up with something different. And I would plan on coming up with something different. So just to be on the safe side. No questions, nothing about the launch site. You guys have been there before, I take it. So
Yeah, we were there last year.
yeah, so you're familiar with it, so that's good. Layout's gonna be a little different, but not much. You know, and we'll have a whole bunch of solid pads. Hopefully solids and hybrids won't conflict with each other. You know, that kind of stuff. So, Bill, do you have any questions?
No, I already shared with the group, you know, that the new arrangement of the pads. My only concern is we're going to have so many so many solid pads in one place that rockets could sit out there for a very long time.
There's that good possibility. There is
Yep.
that possibility.
That's my biggest concern. But we're gonna paint this thing or wrap it in a reflective color. You know, we're not gonna.
Yeah, that's yeah. Hey, white paint, white reflective works pretty well.
Mhm.
Anyway, guys, congratulations. I thoroughly enjoyed the presentation. I thought it was right on. Told me exactly what I needed to do. Filled in the details that weren't necessarily in the report 1 and report 3s. Congratulations on an excellent static test. I'm looking forward to seeing you guys.
Yeah. Thank you. Thank you very much for reviewing.
By the way, you guys, Ben makes his own motors, so I'm sure he'll be excited to see such a big motor going up. So.
Yeah, you got it. All
Yeah.
right, everybody have a good weekend.
One last question for you, Ben, just about
sure.
the recording of this meeting. Do you know if we're supposed to send this to you or what's supposed to be done? I know it said that the meeting had to be recorded, so.
Yeah, you can stop the recording now if you want to. You can send it to me. Yeah, just send it on to me.